All right. Well, time to get started here. My name is Stuart Kinnair. I'm the co-founder and CEO of Interface Fluidics. I'm here today to share some of our insights and stories and case studies of how Interface Fluidics works with our clients to help them reduce their OPEX using their real reservoir fluids to really understand how their particular situation can be improved through the use of appropriate testing. So today for our conversation, the agenda is that we'll give a brief overview of our technology that we use here at Interface. We'll run through two case studies from Canada and one from the United States. And then we will run through our final process here and give 5 key takeaways on how to think about your fluids and how to think about testing when it comes to actually reducing your OPEX. So with that, I'll get started. So Interface Fluidics, we are the world leaders in fast, visual, and repeatable fluid analysis at the pore scale. Our goal is to make fluid analysis as accessible as we possibly can for the engineers in the oil and gas industry to make the best decision they can as fast as possible. Our process at Interface, when we work with you, is to first, we spend a lot of time understanding your process, the goals that you have, and the challenges that you're experiencing. The more time we can spend working with our clients up front, the better the outcomes. And so the number one thing we're doing here is trying to understand what are all aspects of the problem, not just the specific symptoms that we're experiencing, but what are the different potential root causes that need to be investigated and understood in order to move forward. Oh, bad echoes. Okay. I will try and fix that. Hold on one second here. I'm not sure I'm going to be able to fix it very quickly here. Okay. All right. Thanks for the help there, folks. Moving on to the second piece of our process here is really being able to, the unique thing that Interface can do is actually recreate your process or problem using your real reservoir fluids and the data about your geology and your processes. So our microfluidic technology allows us to actually create repeatable methods and repeatable systems to actually investigate systematically the root causes of these fluid issues. The third piece is actually doing that work. So after we've designed and replicated your system, we move on to actually doing the measurements in our laboratory, where we collect all of our data visually and do all of our image analysis and data analysis using our technology platform called Sapphire Lab. And finally, we take all the data and information that we've collected and synthesize that into a report to provide and advise our clients with actionable next steps on what we saw, why we saw it, and what the best next steps are in order to ameliorating the problems that they're experiencing. So at Interface, we have the ability to navigate many different types of issues, many different kinds of fluid challenges. And we've worked with clients all the way from early completion processes all the way through optimization, production strategy, onshore, offshore. So really there's a wealth of places within the oil and gas industry that fluid interactions and fluid properties can really come in and impact production. And Interfaces works throughout that value chain and throughout those fluid interactions. And we have the ability to provide solutions across these areas as well as many more. Now, the question is what is the Interface difference? Why would you work with Interface to solve your fluid challenges versus any of the other well-proven technologies or other technologies that are available out there? And really, it comes down to 3 key aspects. Making sure you represent your reservoir or your system very, very accurately. Temperatures, pressures, porous media characteristics, as well as using real live oil samples or not as is required. But the ability to recreate your system in our facility is something that we can do that really nobody else is able to do. This customization of our technology is enabled by the microfluidics that we use that really can't be seen anywhere else. The second is using your fluids in our system. So reusing high pressure, high temperature, live oil samples when necessary or not when not necessary, but making sure we get the real samples from the real reservoirs, the real field applications allows us to understand and make sure we get good, repeatable results that actually reflect your process. And finally, we have the ability to collect almost all of our data visually. So we use microscopes to take images and videos of how those fluids interact and understand the dynamics over time and how they react to different temperatures and pressures. Visualization and allows us to see pore scale fluid mechanics, fluid behavior, and damage happening, meaning we understand what's going on in much more detail, much faster than traditional testing technologies like core floods and slim tubes and for PVT cells, for example. Now, in the case studies we're going to show today, we're using one of our technologies at Interface called Reservoir Analog. Now, a reservoir analog is a recreation of the porous media that our clients actually have in their reservoirs. So we work with them to recreate the porous media using their data, their geological data, whatever they've got. So, we would start with permeabilities, porosities, pore throat sizes. If they're in a sandstone, looking at sand grain size distribution. If they're in sort of non-sandstone systems, we'll take thin sections and look at sort of morphology of pores and pore throats, as well as recreating the wettability. And so the goal of this is to create a porous media that is representative of our client's system so that when the fluids are in there interacting, they're behaving as they would in the field. The beauty of this is that once we've designed this system, it is entirely repeatable. We can print 1,000 of these, tiny little porous media, and it gives you the same results every single time. And so repeatability and understanding the sensitivity of the fluid system is something that is unique to this because we're able to actually standardize the rock properties, meaning the only variations we see are in the fluids or in the operating conditions that we're experiencing, allowing us to understand more in depth the root cause of these issues that we're talking about. I mentioned before visual analysis. So we use 3 types of imaging at Interface. The first is fluorescence. So whenever you see black and white images with bright white, that's the oil. So that allows us to understand where the oil is going, how it's moving, and how it's interacting. We use bright field imaging, the second picture there, to understand solids deposition, so things like asphaltenes, chemical instabilities, or other kinds of fouling that occur. And the third is using cross-polar microscopy, which allows us to visualize very clearly any crystals. So this is primarily used for wax and understanding how waxes deposit, how waxes form, and how they're changed by the chemistry that we're using. On the right side there, you can see our Sapphire Lab platform. So this is the tool that we actually use to make these measurements. It's about the size of a washing machine and has all of the measurement capabilities that you typically find in a core flood, a PVT cell, a slim tube, and many other tools that you'd find around your standard oil field lab, all condensed into one small package. And then at the bottom of the screen here, you can see an example of the kinds of data that you're getting off of this Sapphire Lab. So what we're looking at here is characterizing how one different surfactant impacted production. And the key thing I want to point out to you here is we've got error bars on this data. So understanding the sensitivity of our results is something that we can do that you can't do in traditional porous media systems. Because we control the porous media, we know that the only variable is the fluids, and so we can report on sensitivity data where others cannot. We do this across a wide range of capabilities. Broadly, we work in the hydraulic fracturing space, understanding hydraulic fracturing fluid compatibility, performance, and damage mechanisms, specifically working on formation damage or skin damage, enhanced oil recovery like polymer flood, water flood, ASP, other wacky stuff that people come up with. And then we also work in the carbon storage space. So understanding how CO2, the impurities therein, interacts with water and the aquifers that we're injecting them into. We also do phase behavior measurements. So full suite of PVT analysis, constant composition expansion measurements, minimum miscibility pressure, diffusion coefficients, viscosity, density, all those kinds of things, as well as we love working on custom, weird one-off problems where we work with folks to really understand a new kind of problem that they haven't seen before. You might have seen us featured in JPT a few times over the years. And so this is an example of when our hydraulic fracturing system was featured in January of 2019. We've worked broadly on many different reservoirs in many different areas. We've worked throughout North America, Europe, Middle East for companies like Total, Equinor, ExxonMobil, Chevron, folks like that. Now, to get into the meat and potatoes here, a few case studies of how people have used Interface's technology to reduce their operating costs. So the first I'd like to go through is Baytex. This is a case study where we were working with Baytex to de-risk a reduction in the polymer that they're using in a polymer flood in western or eastern Alberta, western Saskatchewan, and vet new polymer suppliers with the ultimate goal of finding the best solution to reduce the operating cost of that polymer flood. We're working in the Lloydminster sandstone. So the challenges that Baytex brought to us was that the tools at their disposal broadly left gaps in their knowledge. They wanted to make a change in their polymer suppliers or polymer chemistry, and they didn't feel like they had adequate tools in order to de-risk that change. So in order to make that change, they worked with us to gather additional data to support this decision to lower the polymer viscosity. The reason they didn't use core flooding was because they didn't feel that the data collected from the core floods was going to be repeatable enough to trust, and that the availability of real cores was not easily done because of the challenging nature of the geology. So what I'll show you here is this is a microfluidic reservoir analog that was designed for Baytex. And what you're looking at here is going to be two polymer floods. So you can think of this as a tiny core flood where we're injecting polymer from left to right across the system. And what we're doing in real time is tracking the actual production of oil from that system as a function of the pore volumes injected. And so we're using realistic flow rates from the field. So injecting at the same rates and volumes relatively. And what we ended up with is an understanding of how polymer viscosity impacts the recovery. And so one of the learnings we can take from this slide is that the 50 centipoise polymer produces more oil earlier in the process. But after approximately one pore volume, 20 centipoise actually catches up and your effective recovery factor is not improving any further. So once you've reached that plateau, there's really no benefit to additional high viscosity polymer, and the reduction there looks like it's been it looks to be a safe decision. If we keep going though, to add more information to that process, we want to understand, well, that was a primary polymer flood. Let's have a polymer flood followed by a water flood, which replicates exactly what's going on in their field. So in this, what you're going to see is we're going to inject water to displace the oil, reach an initial recovery factor. And then what you're going to see here is once we switch over to injecting polymer, all the little pink pixels in there, that's showing us not just how much more oil is produced, but which oil that was trapped by the water flood is now being produced by the polymer flood. So this goes beyond just understanding recovery factors. This goes into understanding the amount of oil that is trapped, the mechanisms behind the trapping in your residual oil, and can I mobilize that residual oil? And we see different behavior in residual oil trapping based on many different factors, but chief among them, fluid properties and the porous media itself. So being able to recreate the porous media and use real fluids was critical to understanding the displacement mechanisms in this scenario. Obviously, we did a lot more work here than just what I'm showing you today, but the ultimate result was that Baytex did ultimately reduce their viscosities from 50 centipoise to 30, and then down to 20 centipoise. And they were able to, that's approximately a 60% reduction in their polymer costs. And the actual return on investment working with Interface was approximately 16 times the cost of the project. So this was a no-brainer for them, and they saw significant value in that project. Now, if you'd like to learn more and see the Baytex perspective here, you can look at SBE 212760, where the results of that pilot and our project together were published back in March this year. But ultimately, our microfluidic experiments validated that they could reduce the polymer concentration and maintain their production that they're seeing in the field. We were also able to predict the EUR to make investment decisions for them. So understanding the uplift created by the polymer was validated against other simulation data and other methods. So our data made sense in context with everything else that was going on with Baytex. And finally, being able to reduce this polymer concentration by 60% was obviously a very significant operating return for them, an OPEX reduction. Folks can feel free to drop questions in the chat as I go along here. I'll try and grab them as I can. So our next case study comes from a few years ago. We were working with a client called Primexx, where we were screening hydraulic fracturing additives for both technical as well as economic performance. In this case, we're looking at surfactant additives that are being added into hydraulic fracturing fluids. In order to understand the economic performance of these fracturing additives, we need to understand the technical performance. These are expensive chemistries that, when applied well, can have big impacts, but applied imperfectly can result in challenging economic performance. So this is a Delaware Basin case study. So our client struggled to reduce the fracturing fluid costs without jeopardizing production. They didn't feel like they understood the fracturing fluids performance and the individual component performance well enough to make large changes. They were, as I said, using surfactant chemistry, but the costs on that chemistry are high, and the mechanisms of the performance were unclear. And finally, they lacked the adequate data to verify that the claims that the chemical provider was making and navigate the many variables that are present when you're working with produced water and high temperature systems. And so the goal of this project was to understand, is the surfactant doing what we thought it was doing? And are the manufacturer recommended loadings the appropriate loadings for our well at our time? So what I'll walk you through all the numbers and data on this slide. But the ultimate finding was that switching surfactant providers and changing the loading of that surfactant resulted in higher performance. So I'll walk you through how we get to that conclusion here. So on the right side, we have a table of data. And what we're showing there is the amount of oil that's being produced through our system, similar to the last example where we're just measuring how much oil is produced through the flooding of that system. And you can see, so the number there is the volume of the oil. You can see we have sensitivity on almost all of this data. And so the control is where we have no chemistry. So this is the amount of oil that's produced without adding any chemistry. Now, in each case, we're adding different surfactants, resulting in each of those having different amounts of oil being flowed back, some better, some worse. Ultimately, we can see that sample P4 had the highest volume of oil flowed back, both in high saline or high TDS water or fresh water. In both cases, it performed well. Sample P3, we can see performed quite well in tap water, but in the field, they're moving to this produced water scenario, so it was not an appropriate product to use in the high TDS systems. And so we can see not just that we're producing more oil, but actually using produced water, in this case, improved the performance of the surfactant. And if we look at sample P4, in either of the two scenarios, the two different loading scenarios, we can see we have an increase of about 10 or 15% when we move to these high saline waters. And then at the top, you can see we've run with a 0.5 GPT loading of the surfactant or a 1.5 GPT loading of the surfactant. And by reducing the concentration of the surfactant from 1.5 GPT, which is the manufacturer recommended loading, to 0.5 GPT, we see an increase of almost 100% in terms of the amount of oil being produced. And so this product is producing, sample P4 is producing more oil in a produced water scenario than any other product. And so the Primexx made the decision to switch from what they were previously using, which was sample P1 at 1.5 GPT, to sample P4 at 0.5 GPT. What we saw in the field after this process had been run was that it didn't have a negative impact on production, and they saved multiple hundreds of thousands of dollars on the actual chemistry itself. And so the economic performance of both working with Interface and making this change were very significant, greater than a 10x return on their investment. And so this was able to de-risk the change in their chemistry and understand that there is great variability product to product and water source to water source. So ultimately, their chemical cost was reduced by more than 50%. The loadings were reduced from 1.5 GPT to 0.5 GPT, more than 300% reduction in chemistry. And they also changed that chemistry and found that it didn't hinder their production. So changing vendors as a result of this testing. And finally, we'd like to go through one last case study where we're working with a client to understand wax modifiers, their performance, the way they work and how they work in a production scenario up in the Montney in Alberta. So this operator came to us and they described an issue where they were having wax stabilized emulsions in their production lines as well as in their separator, and they were having trouble having that separator work effectively due to these waxes. They were supplying, or they were using paraffin inhibitors and other emulsion breaking chemistry that was supplied by one of their chemistry suppliers, but the costs were high and the mechanisms and performance were unclear of those chemistries. In the field, they were taking a trial and error approach with different chemistries and could not find something that worked universally and couldn't understand why changes in chemistry actually resulted in the result that they saw in the field. So providing a controlled environment to understand how these chemistries work and why they work was the desired goal, as well as to find the right chemistry for the product or for the problem. So I mentioned before our cross-polar microscopy capabilities. What you're looking at here is a system or a porous media system that has our client's oil in it. And those white dots that you see inside of there, those are the wax crystals that form as we move from well temperature through to production line temperature. I'm going to play this video and you can see we've got here a control where there's been no chemistry added to their oil. Paraffin inhibitor number 1 is in the second box, and then a second paraffin inhibitor on the right. So if you watch, you can see that as we lower temperature in this video, you're going to see that wax crystals appear at the same time in video 1 and video 2. But on paraffin inhibitor number 2 on the right there, you can see we've got significant paraffin deposition in the first 2, but very little in the third. So we start seeing changes in what's going on. Now, to the untrained eye, which is most people, looking at control and paraffin inhibitor number 1 is very challenging to tell the difference. But when we apply our machine vision systems to these tools, we can see actually the results below. So you can see as a temperature compared to wax coverage or wax deposition, chemical 1 and chemical 2 both had significant reductions in the total coverage of wax. But paraffin inhibitor number 2, sorry, drastically reduced the appearance of that wax. And now, one of the things that's not explicit here is that paraffin inhibitor number 1 is a wax crystal modifier, So it's a different kind of chemistry than a paraffin inhibitor 2, which is a wax appearance temperature modifier. So these two products that are both being dosed at the same time have different mechanisms and different performance methods. So when we start looking at, okay, well, now that we know that, we can start understanding, what's going on. We look at the particle size distribution. So how big are these wax crystals and when are they coming out of solution is what we're trying to answer here. And so if we look down at the particle size distribution, both chemistries significantly decrease the average size of your wax crystals, with chemical 2 making them on average very, very small compared to the the control. And so that fundamentally changes how they interact with the rest of the system. And you can see the actual number of wax crystals has dropped drastically, reducing the likelihood of this emulsification. So ultimately, what we were able to do for this operator was quantify the paraffin inhibitor mechanisms as well as their performance. We help them deliver, build a workflow for any future wax issues, so they can come back to us and we can run that same process again for them and help them understand if something's changed, if they want to try something new, and really just rerun that process for them without having to, with it being very low friction. And finally, we gave this operator the confidence to move forward with the chemistry that they ultimately selected. So just to sum up here and provide sort of a quick list of when you're thinking about what can I do about how can interface help me with my OPEX and my fluids. So the first thing to think about is we can validate the strategy that you're applying, whether that's enhanced oil recovery, hydraulic fracturing, or production strategy. You can come to us, bring us what you're doing, and we can look into, well, can we tweak that strategy and understand how to better understand your process. The second is to screen chemistry, whether that is a frac fluid additive or production chemistry. We have the ability to control the fluids and control the process so that we can have these, we can interrogate how these different chemistries interact with the real reservoir fluids, water and oil, to understand where they may be effective or where they may be ineffective, and actually quantify the differences between them. And third, of course, is if you're wondering, how do I quantify the difference between these two chemistries that both appear to be performing really well? Interface has the ability to have more sensitive, our sensitivity is higher than traditional tools, so we can see the difference between high performing products more effectively than traditional tools. This allows you to then optimize your chemical loadings. So whether or not, if you have a chemistry company saying we want to do XYZ as the loading, you'd like a third-party validation to understand the how and the why of that recommendation. We're happy to come in and do that. And then finally, water source compatibility is probably the most common denominator on almost all the projects that we work on, whether that's a polymer flood, ASP, water flood, hydraulic fracturing. All of these are dominated by complex waters and water sourcing, which is expensive and time consuming. And so making sure you get your water sourcing correct so that you don't have any adverse effects on your production later down the line is really critical, whether that's part of your planning process or understanding or remediating problems that you see during your production. So with that, I'll open it up for questions. And thank you very much for your attendance and for your attention. So I've got a question here from Stan. Any idea why the wax crystals don't form in the same location? In those videos, we have clean samples. So we have different samples in each scenario, and the likelihood of where the wax is going to crystallize and nucleate is really a random process. So you can't predict it. That's part of why we have a wide view there, and we're trying to capture as much sample as possible so that we have as many wax crystals appearing as possible, as quickly as possible, and so that we can understand the distribution and really put sensitivity around that. So it's about getting more waxes and more areal coverage. For those of you, someone's asking about the recording. This will be posted to YouTube, our YouTube channel, in the coming week or so. with closed captions and translations and all of that. All right. I don't see any more questions coming in here. I'll let you all go and say thank you very much and look forward to reaching out. If you want to reach out to me, my phone number and my email address are on my LinkedIn profile, or you can send a question to info@interfacefluidics.com or reach out to any of our team members on LinkedIn. We'd be happy to chat with you and learn more about the challenges that you're working on. Thanks, everybody. Have a great morning. Bye.